Okay, thank you. So I'd like to present results that were obtained by Audrey Krokowiak and myself on this admittedly crazy high TC material. And yes, in the previous discussion, you hit on many of the issues that we have in creating these superhydrides. We're at ridiculous pressures, temperatures needed are obscene, and the samples are inhomogeneous. But I think with the more recent data that's come out on H3S and CaH6, it's clear that we can make a claim to this very high superconducting material. So I put up here the collaborators in this because without everybody here, it would not have happened. I want to point to a few people, though, that really made this possible. I'll start with Mukhtar Ahart, who is in Russ Hemley's group. He took Audrey under wing and taught her how to load the cells and synthesize the material. And without him, this would not have happened. Tony Helm is at Dresden, the pulse field facility, and he and Audrey and I have worked together previously on some of the 115 materials where he used his ability with FIB to define electrodes and a device so that we could do pulse field studies, excuse me, on the 115 materials. Vaughn Williams, Morgan Olaf were critical on the technical end in designing and fabricating the cells. Neil, everyone knows, I don't need to point to him, but Konstantin Glazerin was critical in helping Audrey obtain the necessary X-ray data after we finally reached 556 Kelvin. The cells we have are not ideal for X-ray studies. DAISY was at the time the only facility where we could obtain the data. Now ESRF has been reconfigured and can do the same. And the last person that I want to point out, obviously, is Audrey. She was the one who did, I was there assembling cells, we were working together, but she was the one who learned everything that Mukhtar readily taught her, and eventually brought that sample back to Tallahassee and was doing the measurement on the PPMS system that we have here while having a beer over at Proof and remotely dialing in when she saw that transition, and called in and said, "Holy moly!" And I was the one who, for 3 months, said, "You got to convince me," and she did over time. So this is her discovery. She truly owns it, and she's the one that should be recognized for it. So there are a couple slides up front that I want to discuss because they point to how difficult this synthesis is, and also point to the fact that non-zero resistance, even below the transition, is common when using AB, and common sometimes just when looking at elemental materials too. This work is that of Arametz and Drozdoff. It's just, this was an amazing discovery, right? The Arametz is, he's a workhorse. So my hat's off to him. But the initial synthesis was very complicated. Chemistry going on. Here you see that there's a transition. It looks somewhat like the sulfur transition, and only after working it back and forth a few times in temperature do they see indeed the sulfur transition at high pressures, and then this transition at 185, and then with additional annealing and increases of pressure, they were able to get the resistance to drop to 0. And then you can see in this final trace here, just this beautiful family of curves that they were able to obtain. But at the same time, they started over here, right? And it just points to how difficult these measurements are, both defining an electrical circuit, getting a sample to grow, and hydrostatic conditions. They're typically plus minus 5 GPa, which isn't a lot when you're up at 140 GPa, but it's still there. It strains the sample, and that leads to broadening of the transition, as I'll show shortly. And then recently, in the last month, Osman and Friedman published on H3S. They attempted 11 loads, my apologies, with H2S, as Arametz and Drozdoff did. and failed miserably on all of them, according to Friedemann. And then finally turned to the use of AB, ammonium borane, and were successful immediately. But they also found, as you can see in this depiction of the micrograph here, you have the material of interest in red. You've got blue, which is sulfur, and in these gray regions are the electrodes pushing in. And indeed, that's exactly, I mean, this is, you look at that and you realize you're only going to see the superconducting material if you look across a couple select electrodes or see it robustly. And that's what happens here, right? The blue trace is just looking at the high pressure sulfur prior to laser heating. And then after laser heating, this red trace is looking across these two voltage taps, applying current across here, and they see pretty clearly this H3S material, but they also still see some sulfur here, right down at the very low TC. And then if you look across these taps, you see mostly sulfur, which is understandable, but then it does reach into and sample the superconducting material. So again, it points to when AB is used as a hydrogen source and pressure medium, it's both non-hydrostatic and you end up with inhomogeneous growth. And then recently there were two very nice studies of calcium H6, completely independent studies and completely consistent results, one by Lee and one by Ma. We heard from Ma yesterday, and beautiful talk and extraordinary results, both theoretical and experimental. But you can see with Lee, he has a multi-phase transition, which is typical for when one uses AB. And also there's background below TC that is non-zero. If you extend far enough, you're not going to get to zero with this material. And Ma his group loaded many cells. Some showed zero resistance. I'm showing the ones that don't, just because they go to the point that when using AB as the hydrogen source and pressure medium, often you end up with non-zero resistance, as Ma finds here. But it's clearly a superconducting transition, because if you apply magnetic field, you get the suppression. Not as much as people would like to see. They don't see the broadening that they want to, but again, we're up at fairly high temperature, and so one shouldn't expect to see that much broadening. And then the last one, I'm going back to the cuprates, because that's what I cut my teeth on, was YBCO. And Paul Chu's group's results on mercury, the mercury cuprate, where when they did hydrostatic studies up to 17 kilobar in a piston cylinder cell, they saw reasonably sharp transitions and zero resistance. But when they extended that pressure range up to 150 kilobar so that they could push TC out, you see the issue becomes you're at 10 kilobar in the diamond cell, reasonably narrow transition, but not as narrow as one has down here with the hydrostatic pressure medium. And then as one pushes out to 50 and 150 kilobar, it's non-zero and it's very broad. And that it's not unreasonable to expect that. You've got a reasonable gradient of pressure in a cell at that point, and it's just going to get a bit messy. But for this discovery research, that is what we're up against. We're pushing the limits, and we're just not going to have that perfect data set at this point, which unfortunately for theorists, they don't want to hear that, because you folks need the data to understand what's going on. We'll get there. It's just going to take some time. So our jumping off point was that we wanted to look at lanthanum H10 and lanthanum H6 and use the high fields here to try to get a handle on some of the underlying physics. It was a pretty well-controlled experiment. We had a cell at 162 GPa and another cell at 175 GPa so that we could touch both those stoichiometries, but it went wonderfully wacky, and instead we ended up with this 556 Kelvin superconductor. But our colleagues, discovered LaH10 along with Arametz's group, and I show the data here from that PRL paper of Samadhi Zulu's, or Zulu, or Z, depending on how well you know him. And again, you can see in the data set here that they had that below TC there is a monotonically decreasing resistance, and it doesn't go to zero. But but they had data on pure lanthanum, and because of that, they were able to subtract out or normalize the resistance and then subtract that out because they had data that clearly showed that this was a contribution from lanthanum. All right. So our methods, just to give you a quick rundown on that, I designed a cell based on Arametz's beautiful design that he published in his book that every experimental high pressure theorist, I think, or every high pressure experimentalist has. And it worked beautifully. It's very small. It's 9.5 millimeter in diameter, 39 millimeter long. Uses this very nice Russian spring and is crazy stable. After a year and a half, the pressure of a 175 was maintained throughout that year and a half that the cell was alive until it finally died from hydrogen diffusion into the anvils. So we have the small cell. We do what other folks have done. In this case, the gold leads or the tungsten leads that folks use are replaced by the fibbed electrodes that are shown here on top of the anvil and running down the pavilion, and then the sample is tacked to those electrodes, and AB is introduced. Pressure is brought up, and then we laser heat from one side. You can see the sample here. We'll be seeing this micrograph a lot. The sample's smeared. It was a little too thick, and it's smeared off to one side of the culet. And we can see the issue with that is we sheared two of these leads because they didn't have any lanthanum on top of them. But our starting point was, I show here a micrograph looking through a diamond anvil cell. This is extremely large culets, 540 micron culets. But this is work that Audrey did on the fermiology of YBCO when we pushed into the overdope state of YBCO to look at the fermiology in this material. And she was successful in seeing quantum oscillations up to 25 GPa. And but unfortunately, we didn't see any type of reconstruction of the Fermi surface. So, or fortunately, because it flies in the face of what has been proposed. So we have these defined electrodes. We're using ammonium boring, laser heating. All of this work was done at APS HP CAT under the guidance again of Mukhtar Ehart and Zulu. We had two cells, one made or synthesized, the other did not. Fortunately for us, because when Audrey tried to laser synthesize that material, we saw a bright flash, and Ravi told us we needed to stop because most likely it broke. That was an indication that we had broken the diamonds. It was the best thing that we could have done because that gives us our control cell, and that cell is B003. The cell that made this superhydride is B002, and I'll refer to them that way in the talk. Okay, so now again we're back to that micrograph of the sample. You can see the lanthanum. It just touches the two electrodes here and here, so we're able to do a couple permutations of current and voltage, and all of them show the same result, but at different amplitudes. Okay, and then as far as the laser heating, Friedemann realized that it might be best to defocus his laser beam, and he did that. He defocused to about a 20 micron spot. We did not do that. We had pretty tight spots. Well, we had 20 microns. Sorry, his was larger. I think it was 60. But then we rastered across in a very discrete square pattern. So we came across here, we hit it about 4 to 5 times, and then moved over, hit it 4 to 5 times, and continued across the sample that was of interest between the electrodes. Again, this was fortuitous because Mukhtar had to go home. COVID was coming. He had a cold, and Yue Meng sent him home because we were all scared to death. And I didn't transfer the information to Audrey that said, under no circumstances, hit one spot more than 3 times or something weird happens, was his instruction to me, which I walked in exhausted and didn't convey to Audrey. And so she hit it about 4 to 5 times per spot. That could have been something and we're gonna have to go back and do a controlled experiment to see if indeed that contributed to our result. These are the initial results that she obtained. In the PPMS, you can see here she's cooling down pretty quickly because we're thinking if we're going to see anything, it's about 270 Kelvin. And all of a sudden we see this transition here. She immediately backed up, warmed it up a little bit, about the same 1 Kelvin per minute, went through that transition again. We have a hysteresis, which our PPMS thermometer is not connected to our diamond cell. So we're going to see a hysteresis here. That's understandable. But then when she slowed down again, we came back through and you saw exactly at exactly the same point, the transition again. This is me screwing with the darn PPMS and we lost data here. So there's nothing there. But importantly, there's also nothing in this range here where we would see, if we had LAH10, we would have seen a transition. This configuration is current across these two tap voltage, or these two electrodes, and voltage being measured here. So in this region, we see this very interesting material. And it's also at 10 microamps. We were concerned that we were going to damage the sample, so we switched and went down to 600 nanoamps and also changed configurations so we could look at two permutations. As to whether we can see superconductivity with these electrodes and with the fact that the lanthanum was smeared off to the side, we have this controlled cell, B003, where we can cool it down. We see nothing in the range of where one might see any the lanthanum hydrides, but at very low temperatures where one should see lanthanum and D, we see just that, right? However, it is also non-zero because we're going through some interesting material, or the circuit's not quite right. This is data for B002 after we had increased the temperature, and you can see here, this is the transition. And again, at the lowest temperatures, we see the little bit that's associated with the lanthanum superconductivity at very high pressures. So it is obviously that the electrical circuit is viable for measuring TC. You can see the transitions up here blown up in the synset. And then if we, to verify that it's superconductivity in this low temperature region, we apply magnetic field. You can see there are several transitions here, most likely due to the fact that we have a non-hydrostatic condition in that cell, plus minus 5 GPa. But they clearly are suppressed and they fit reasonably well to a GL fit. So going back to B002, this material that made this interesting 556 Kelvin superconductor after many thermal excursions, we have the original data here in blue with the first electrode, and then we have this data after we've taken that same sample and gone through some thermal excursions. No longer do we see the transition at 294. It has moved out, right? We can go all the way down in temperature. We do not see any transition associated with lower stoichiometric material of any type. That configuration that we're looking at is this second configuration here, where the current is across the extreme electrodes that are in touch with the sample, and then tapping into V1B1 here and looking here. And again, so we're seeing the same transition, and it's in a different region. The first one, the blue, is this region here. And now we're seeing this same interesting material in the region above it, okay? And then if we apply in this family of, or in that last curve, I'm sorry, go back here. If we look at this one and apply magnetic field, we can see very, very subtle and almost non-existent shift in the cooling trace, which are the dotted lines. And in the warming trace, we do see a suppression of the field. And then for the third point of interest that we picked is essentially where the cool down and warm up traces converge. And we see something that looks possibly like the melting of a vortex glass, the fit. It does not fit GL whatsoever. But interestingly enough, something that needs to be pointed out in these traces here is, as we warm up, that's when we're starting to evolve more hydrogen, we believe, and also possibly introducing more material into the lanthanum hydride other than hydrogen. You can see there's a multi-phase composition here, but as we cool down, it smooths out. And in fact, each time we go up, this was the first trace, 0T, and then we went up to 2T, 10T, and then 16T. Each time we go through and up to max temperature, things start to smooth out. There are fewer transitions in this warm-up trace, smoother cool down, and here it's a little sloppier. admittedly, but the cool down is clean. And by the time we get up here, it's almost a clean transition, and the cool down is quite clean. So it's chemistry in action, or possibly electrochemistry in action at that point. What I've done in this slide, this final slide of these thermal excursions, is to show how we moved out. Not only does the amplitude increase as we go through these thermal excursions, but also the transition width. And in fact, at about, see, I got the correct one, the red trace, so about or the yellow trace, about 500 degrees Kelvin, we really start to see a broadening of the transition in many phases being coming into play. And I suspect that has to have something to do with either diffusion rate or activation of the release of the hydrogen or incorporation of this other material that's making this interesting 556 Kelvin superconductor. So again, the transition is completely irreversible. We can go down in temperature. We do not see it at any temperature. You can see here in all these traces, they all fall on top of each other with the exception of the red trace. But the interesting thing is that at about 600 Kelvin, which is the max that we went to, we're about half the temperature that is achieved when we were heating the sample locally with the laser. And that, I think, goes to the fact that we are releasing the hydrogen. And I have tacked the two final curves, the 530 and the 580 together here when I do my square. The 580 is where everything failed. Solders failed, epoxies failed. They aren't meant to go that high in temperature. And we see that in this trace here where we are coming down, and the heaters which were soldered to the external wires, those solder joints failed. We lost continuity and the sample just ripped down. We also lost the sample because it also had solder joints on it. But
sorry, Stan, you have still 4 minutes.
Yep, these two traces fall pretty close to one another, so I grouped them together. Okay, these are all three configurations. This tap, this set of taps, this set of taps. You can see they all show similar traces. So we're seeing this material in all of them. So Audrey, at that point, a couple months later, went to DAISY, obtained the X-ray data. I'm going to show data looking across this line. Later, we're going to look at the star first, where we see FCC and rhombohedral LAHX. We also see a platinum H8 and residual lanthanum and platinum. So we have a mess in there, but the good thing is we also have markers. These markers for lanthanum and platinum fall right on 175 GPa if you do the volume reductions. And we also find the same thing. Oh, I switched these two, my apologies. B002 is this one, B003 is this one. Okay, so it all jibes. We have X-ray confirmation of our pressure. We also have X-ray confirmation of the fact that it's an inhomogeneous mix. If from the star we move out away from that star, we find that the composition changes dramatically, both in X and also in Y. So this is going to lead to that very broad transition that we see, and also the non-zero behavior. And then the arrow that I showed, now we're looking, the arrow was horizontal, but now we're looking across here in this waterfall. These are three discrete synthetic or laser spots, and you can see that the synthesis was discrete and very different in these three spots. Again, that would cause issues with non-zero and the broad background below TC. So I've gone through all of this, what allows us to make the claim. X-ray verifies everything. Inhomogeneous growth validates the pressure and points to this distorted lanthanum hydride backbone. And then, we have to start out with this initial 294 Kelvin transition, and with thermal excursions move out to 556 Kelvin. So I'll put this slide up as, everybody knows what we need to do, and we need to reproduce. We're trying to do that now. We've shrunk the diamond anvil cell. This is the latest version coming off. This is a cell that will that's about the size of a 1 cent euro piece. And this is going to allow us to do rotation and pulse magnets, so we can look at HC as a function of angle. There are many other things we can do. We have plastic diamond amble cells too that we hope to use to do fermiology studies if we can get the pressure down somewhat. But I just wanted to leave you with this final slide. This is Mukhtar instructing Audrey on how to load the cell, and Mukhtar and myself having way too much fun trying to increase the pressure on one of the cells. And then this B002, the sample that, or the cell that had the sample that was 556 Kelvin, is shown here after the run. A little worse for wear. And this is the data point that I'm hoping you'll all start including on your plots at some point, with CSH down here and some other interesting materials to come soon. Thank you very much.